Okay, so good morning everyone. Thank you for having me today. I will present my work that I did during my 6-month internship with Professor Serena Villatta in collaboration with Professor Stefano Faralli from the Sapienza University of Rome. So I will start by giving a brief introduction, and later I will explain the methodology and the experiment we conducted. I will also show you some results, and I'll finish with a brief conclusion and some future work. So today, with the spread of misinformation and manipulative speaking, it's becoming even more important to uncover hidden strategies and logical fallacies behind someone's speech. With this goal in mind, we look into the contemporary field of argument mining that deals with the analysis of arguments. In particular, argument mining has been applied to various areas, and we want to focus in political debates that represent an extremely challenging scenario. This led to our research question: can we incorporate structural knowledge underlying argumentation graph from political debates to enhance the current state of the art in relation prediction argument mining? But first, let's make a step back. What is argument mining? Argument mining is a research area that deals with the analysis of arguments, and this task can be further split into argument component detection and argument relation detection. Argument component detection deals with the prediction of the type of argument that can be either claim or premise, and identification of the boundaries of the argument. On the other side, argument relation detection deals with the prediction of the type of the relation between arguments that can be support, attack, or equivalent. This particularly, we will focus on this last task, that is argument relation prediction. But how can we leverage contextual knowledge? In this area, many studies have been made by using pre-trained LLMs that are able to capture rich contextual semantics and enable an accurate representation of arguments. On the other side, how can we leverage structural knowledge? To reply to this question, we used knowledge graph, which are type of graph specialized in representing structural knowledge. To leverage this type of graphs, we use knowledge graph embeddings, which are models whose goal is to create a dense representation of a graph in a continuous low-dimensional vector space. In particular, the family of KGE models that we used were translational, semantic matching, and neural network-based. To go forward with our study, we chose as a dataset the most comprehensive collection of US televised political debates from 1960 to 2020. This dataset has been annotated with both argument boundaries and type and argument relations, the ELEC DEB 60-20 dataset. But we needed a formal way to represent this dataset, a way that could be comprehensible to these KGE models we wanted to use. Therefore, we decided to represent argument as triples. A triple consists of 3 parts: a head entity, a relation, and a tail entity. The relation connects the head and the tail entity. In this case, the head and tail entity are represented by arguments, and the relation is the relation connecting them that, as I said before, can either be support, attack, or equivalence. Let's make an example. In this speech, extracted from the Obama against Romney debate of the 3rd October 2012, I've highlighted in italic the premises and in bold the claims. Now, if we want to make a triple out of this speech, we could do the following. Choose as head the premise if we lower that rate, the relation is support, and the tail is the claim they will be able to hire more people. By using this formalism, we were able to represent the whole dataset as a series of triples. So first of all, we started with the generation of the knowledge graph, and later we evaluated this knowledge graph with the KGE models I showed you before. We evaluated these models using various tasks, such as link prediction and deletion, triple classification, and so on. We tried also some performance enhancement measures, such as using pre-trained embeddings. Finally, we arrived to the response of our research question by proposing an approach that combines a fine-tuned large language model with a knowledge graph embedding technique to leverage both structural and contextual knowledge. So first of all, when generating a knowledge graph, we had some problems. First of all, the sparsity, because politicians, when they make their speeches, their claims are usually supported by only a few premises. Also, topics in a debate change frequently, and therefore there are sporadic connections from topic to topic, and this led to a sparse graph. Our solution to this problem was to incorporate additional information, such as the speaker, the year of the debate, and the type of argument. Of course, we incorporated this additional information in a form of triples, and we made a custom relation to incorporate this additional information. This led to the creation of 12 different graph permutations. In particular, I want to show you in the bottom of the slide, we also tried a different approach for the basic argument triples. Instead of using argument, relation, argument, we incorporated in the head and tail entity also the type of the argument. So we went from argument, relation, argument to concatenation of argument type, relation, concatenation of argument and type. And this led to the creation of other permutation that we exploited also. So as I said before, the first benchmark included an evaluation of all these 12 permutations with trans-C, dismult, and conv. In the task, there are link relation prediction and link deletion evaluated with IZK, mean rank, and mean reciprocal rank, and triplet relation classification evaluated with macro positive and negative F1 score. First, our first benchmark included the training evaluation of all kinds of triples, but we were only interested in some particular triples, which were the ones where the relation was either support, attack, or equivalence. Therefore, we focused on this triple during the second benchmark. In other words, we continued training on all types of triples, but we only evaluated the one of interest. Then, as I said before, we incorporated pre-trained sentence embedding using SentenceBERT, which is a modified BERT network that outputs more accurate sentence embedding for the entities. And then we identified the optimal knowledge graph embedding model and its optimal knowledge graph configuration. Finally, we arrived to the approach, which is the combination of fine-tuned LLM and a knowledge graph embedding model that which output a prediction of the relation that goes into a meta-learner that outputs a final relation. We collected numerous results, but the time won't allow me to show you all, so I want you to focus on this triple classification task. So in general, let's look at the first benchmark. The performance of all models increased when adding additional information. So this is good for us, but we wanted to focus, as I said before, only on certain kind of triples. In this second benchmark, we can see there is a small drop in the performance, but this is normal since the triple we're interested in are only the minority group of the dataset. Therefore, the model focused on other relation rather than the one we were interested in. To correct this problem, we try some performance enhancement, such as including additional pre-trained embeddings. This is what we did in this third benchmark. We can see that there are small improvements in some configuration for some models, in particular the semantic matching dismult. But finally, how to choose the best KG model? We look into the robustness to noise of these models, some improvement and difference in similar models, and we perform an error analysis. To perform this study, we use the top 3 KG permutation, meaning the permutation of the graph who showed the best results in all tasks. So first of all, the evaluation of robustness to noise. We can see that the conv model is not very good when noise is inserted into the dataset. By inserting noise into the dataset, I mean that there were inserted erroneous triple in the dataset, which the model didn't know about. We can also see that trans-C dismult model behave better and still have an acceptable performance when increasing the noise. In particular, this mult is slightly better than the Transient model. Then we evaluated similar models, and we can see that models of the same family have a similar performance. In particular, it was shown that the TransH model is the best one in the translational family, as the DisMult and the Conv model for their families. Finally, the error analysis. This was the most important analysis we made because we were able to understand many things. For example, the Transient model in the third settings behave well in the relation prediction task, but if we look at the prediction of each label, we can see that it's completely biased toward the support relation and doesn't pay any attention to the equivalent relation. Other models, such as Conv, were not able to train properly in some settings and were completely ignoring sometimes both support and equivalent relation. In the end, the DisMult model proved to be the most balanced, with a good relation prediction Z1 and a good relation classification F1 macro, giving attention to all three labels. Of course, the equivalent was the one to which the model paid less attention because it was underrepresented in the dataset, but this is to be expected once again. For all these reasons, we choose the DisMult model as the best performing KGA models, also because the optimal setting for this model of the knowledge graph was the one with modified argument nodes that included the year information. This kind of dataset contains less triples than others that include other kind of information. For example, let's think about the permutation that includes both speaker, year, and type. So the optimal setting for this model, the optimal KG setting for this model included less information and were allowed this model to train faster for this dataset. Now let's reply to our research question. As I showed you in the pipeline before, we combined the two models, LLM and KG, using a meta-learner. The results are shown in this slide. As we can see, the Roberta model alone only reached a 60.3 F1 macro score in the argument relation classification, and this model reaches 60.4, while the combination of the two reached 68.3. As a meta-learner, we used a random forest classifier in this case. We also used other types of LLMs, such as the Berta, that only alone reach a 69.4, but in combination with the DisMult model, reach a 73.4. In this case, we used a CNN as meta-learner, and this meta-learner also has in its input the head and tail entity, so not only the prediction of the other two models, but also the arguments of the triple. In conclusion, this was the first time the structural knowledge of the ELEC-DEB 6220 dataset was used. We made an in-depth study of the limitation of the KG, an extensive benchmark of 12 different permutations of the KG, reaching an increase of the state of the art for the prediction of argument relation in political debates. If you want to look at some future work, our goal is to use Kepler and KG-BERT, which are frameworks that train in conjunction a LLM and a graph model for this purpose, while our approach trains a LLM and KG not together, and then trains a third model. Therefore, we want to exploit also this other kind of approach in our future work. Another thing is that we want to use custom losses that take into account the imbalance in the dataset for our KG model. Thank you for the attention.